All right, I'm going to demonstrate now the Lab 5 for you. Hopefully it records properly this time. So in Lab 5, we are looking at JK flip-flops and kind of exploring how they work and using LEDs to represent the different output states. Um, so here, I'll kind of go over some of the components that we can see. So we've got two resistors here. So these are going to be current limiting resistors. Those are basically managing the voltage coming through this diode. And then we've got pull down resistors here. All of these 1K resistors are going to be pull downs, so they're connected to ground, and those are basically happening on each of our inputs. For the JK flip-flop, we're using a SN74F112D. And so I've labeled all of these switches accordingly. So we've got our preset. So this will cause resetting of the system here. A is going to be connected to our clock. So you'll see on clock pulses, which you can kind of see in this truth table, on clock pulses, that's what triggers everything. That's why it's labeled trigger. And then we've got J and K, obviously two inputs to the JK flip-flop. And then we've also got C here, which is going to be our clear. So in the initial state, we want to have clear closed, and then we want to have our preset also closed. So if we start running the simulation, so we'll see initially that it's in set mode. So the initial configuration that I've got here, we've got both J and K closed. So when I change the state of A, which is our clock, we can see that the LEDs between the set and reset are going to alternate back and forth, which when we come down to our truth table, when we have 1, 1 on J and K, we have a toggle inference. So that's what's going to happen when they're both closed. So if I then open up J and we flip A, we can see that J, when it's open, will basically allow K to reset the system. So when J is 0 and K is 1, we get a reset. So that's why our reset LED is high. And if we swap that, we can now see that even though I'm flipping our clock, it is consistently on the set. So we've got J is 1, K is 0, and we're inferring a set from that. So this kind of shows how the different input states of these can allow for the system to basically act in one of these states or in a state where it can flip-flop between them. I'll now show when J and K are both open, we see there's no change. However, if I flip this over here and open it, there's again no change. So when these are open, it basically maintains whatever state it was initially in. So again, we can see that in our truth table. When we have 0, 0, we get no change in state. And again, we can look at kind of the existing states of Q. So it's all dependent on what our Q values are at the initial state. So, if Q starts at 0 and Q prime is obviously going to be the opposite of that, it'll be 1. And then as we actuate it, it's going to change, but that change doesn't actually have an effect because again, when they're both 0, we have no change in our output from the JK. Another thing that I wanted to point out is if I close both of these, so you see that these are changing again. Now, if we watch A as it opens and closes, you'll notice that it basically takes two movements for it to actually change. So we're currently on set. If I close it, nothing happens. It only happens when I reopen it. And again, when I reopen this switch, that's when it's going to do it. So basically what this means is um, here it's in a closed state, so we can treat that as high since it's getting the power signal from VCC. So what's happening is when it drops low, that's what's triggering the change. So it's that falling edge that is actually triggering the clock here and what's being picked up to actually actuate the JK flip-flop. So that's enough of this one. Let's go on to the second part of this. So here we've got two JK flip-flops connected, and basically we're supplying that with a square wave generator. So we're supplying the wave into our clock, and so basically that's gonna obviously alternate between high and low. And so, like I showed before, on those falling edges, this JK flip-flop is going to have an output. Now the output from Q is going to feed into the clock of the next JK flip-flop. And so basically what we'll see is this first LED will flash very fast. It's going to replicate the exact function coming out of our function generator. And then, sorry, I missed one thing. We've got VCC connected to both J and K on each of these. And so that's obviously just allowing this to flip-flop between set and reset. So because we've got it both set high, it'll always be allowed to flip-flop between them, which is an important feature there. So yeah, this first LED will replicate the function coming out of that. It will then go through this JK, and then the next one will replicate essentially half of that. So because the JK, you'll have the first one activate Q, and then the second one will activate Q prime on that trailing edge. Basically, the speed of this turning on will be half of what this was. So essentially, what we can do is we can step down the speed of each of these LEDs and their flashing, and control that using the JK flip-flop here. And so in this configuration, we'll go from, let's say, 100% speed to 50% speed to then 25% speed, because it's halved again after this one. And so if we return to this one, we can see how when we swap A, right, you get this one high, on the next stage, this one is high. Well, since we've only got the LEDs connected to Q, basically it takes, it makes this set basically disappear. So you've only got that reset showing up. So basically every other time it will illuminate it. And again, that's why we basically lower the speed by a half. So if we go and run this now, just make sure this guy's stopped. So we'll go and run this, and you can see, like I mentioned, the first LED is going extremely fast. You know, it looks like it's almost consistently high. This one, you can clearly see there's a solid on and off flash, and then this one you see a very delayed flash. And so that's exactly how we can kind of chain JK flip-flops together and create this system where it slows things down quite a bit.